Welcome back, guys. We're going to talk about inverse matrices now. We have the identity matrix, and we're going to define what that is. So, if you want to know what an identity matrix is, if you're looking at a square, identity matrices are square matrices. So, if you have 1, 0, 0, 1, that is the identity matrix of a 2 by 2 matrix. If you want the identity matrix for a 3 by 3, then it's 1, 0, 0. 0, 1, 0, 0, 0, 1. And this, of course, is 3 by 3. And if you did 4 by 4, all you're going to notice is that this diagonal is going to have 1s and everything else is a 0. And so when you get that, that is called the identity. The reason it's called the identity is because if you multiply that matrix to any matrix of the same size and shape, or I'm sorry, not of the same size and shape, of the same, if you multiply this matrix where it actually does multiply, then you will get back the original matrix you started with. And so that's why this is called the identity matrix. But there's a little bit more to this. So show that B is multiplicative inverse. I'm looking at this, of course. And we want to show that this happens. These are multiplicative inverses of each other. Okay, so I'll copy that. To do this, we are simply going to multiply them together, and you're going to see that you get the inverse, or the identity matrix. Come on. Doesn't like me right now. Is this a joke? There it goes. Okay. So we're going to multiply them together. Oops. We have -1, 3, 2, -5. 5, 3, 2, and 1. So we have, let's multiply. We have -1 times 5. So I'm multiplying this row to this column. And then plus 3 times 2. That's the first entry. Then we're going to do this row and this column. That's -1 times 3 and plus 3 times 1. Next one, we're going to do this row by this column. That's going to be 2 times 5 plus -5 times 2. And then, oh yeah, there's that trick we were using. So let's do it. This is going to be 3 and 1, 2 and -5. Okay, so let's calculate. This top corner, that's 6 minus 5, which is 1. -3 plus 3, that's 0. 10 and -10, that's 0. And then 6 and -5, that's 1. So we got the inverse. So what that means is A times A inverse is equal to I. But if we want to be able to say these are for sure inverses of one another, we have to multiply them the other way. Remember, multiplication of matrices is not commutative in general, so we're going to go the other way this time. So instead of doing that matrix, we've shown that one. Now we're going to go the other way. So let me write these again real quick. We're going to do 5, 3, 2, 1. -1, 3, 2, -5. And we're going to do the same process, but now we're showing A inverse A. So this is obviously A inverse. This one's A, so now it's A inverse times A. So here we go. This row, this column. So this is going to be 5, -1, and plus 3 and 2. Top corner. Okay, then the next row is going to be 5 times 3 plus 3 times -5. That's that corner. Then we have 2, -1 plus 1, 2. Yeah, that's good. And then we have 2 and 1, 3, and -5. So this is going to be 6 minus 5, which is 1. 15 minus 15 is 0. -2 and 2 is 0. 6 and 5, -5 is 1. So now we have shown that A inverse is equal to A inverse A, which is all equal to I. And therefore, we have that these two must be inverses. So what I'm saying is that the two matrices they gave us must be inverses of one another if that happens. There's only one inverse. You'll never have more than one. So a nice thing about inverse matrices, so if you notice, if we have the following, if we write our matrix A times X is equal to B, and so this is just like your system of equations. You have A11, A12, A21, and A22. And then you have X1, Y1, that's how you'd see it, is equal to the solutions, which are, I don't know, let's say these are B1 and B2. Then if we left multiply by A inverse, so important thing to note, when you do left multiplication, you are doing it on the left. So if you do it on the left there, then you cannot do it on the right on the other side. So what this looks like is here is that's A inverse and A inverse. Okay, so we know this is I, and anything times I is X, or I'm sorry, anything times I is going to be itself, A inverse B, which means that X is equal to A inverse B. And so what that means is if we take the inverse of this matrix and multiply it to these solutions, we will get these are the solutions to the system. So what I'm talking about is if you have X plus Y is equal to 3, and I don't know, let's say 2X minus Y is equal to 4, then when you do the inverse of this coefficient matrix and multiply it to these solutions, you'll get the values for X and Y. It's another method similar to Cramer's rule of solving systems of equations. So that's one important application of these inverse matrices. You can use them to find the solutions to the system. Okay, so that's taken care of. Now there is a formula, and I'm going to show you it. The reason I did this in a different way the first time was because I didn't want to talk about the determinant and just say, oh, it's AD times minus BC, because that's what this technically is. But what this formula is if you have matrix A, B, C, D, then A inverse is 1 over the determinant of A times, and then obviously notice they negated B and C and they switched A and D. That's a standard way of doing this. I'm going to show you two methods of doing this. One involves Gauss-Jordan elimination if you're good at it, and then the other one is this way. And so let's go and do this for some of these problems real quick. Let's do them for these 2x2s down here. Okay, so we've got clear canvas. Okay, so we've got our formula and we've got matrix A. 2, 3, -1, 2. Now, one thing to note, if the determinant is equal to 0, that's bad, because you notice in this, we're dividing by 0 if that's the case, and you can't divide by 0, so if the determinant's equal to 0, then matrix A is said to be not invertible. Okay, so you can't invert it if the determinant is 0. Not all matrices are invertible. Okay, so let's figure this out. We're going to use the formula. Let's do the determinant. This times this is 4 minus this times that. 3 times -1 is -3, which I believe is -7. So this is going to be 1 over 7. Okay, and so we've got what we're going to do now is we're going to switch A and D, these two. Well, they're both 2, so they don't switch actually. We don't notice that they switched. And then we're going to negate these two. So these are going to be -3 and +1 now. And then all we're going to do is distribute that 1/7. So that's 2/7, -3/7, 1/7, and 2/7. And this is your inverse matrix. If you want to check it, all you're going to do is you're going to multiply them together and verify it. Okay, that's what it says to do, but we're not going to do that step. We did that earlier in the video. If you want to try it. It should work out fairly nicely. You should be able to tell right away that it's equal to 7. Or I'm sorry, that it's equal to 1001. Let's do 14 now. We've got 0, 3, 4, -2. Okay, so we want to find the determinant. That's going to be 0 times 2 is 0, minus 3 times 4 was 12. Okay, so -12 is the determinant. So we have 1 over -12. And then we're going to switch this one and this one. So that's going to be -2 and 0. And then negate the other two. So change their sign. -3 and now -4. So this is equal to -2 over -12. -3 over -12. -4 over -12. And 0 over -12. Which is 1/6, 1/4, 1/3, and 0. And that will be your inverse matrix for matrix A above the number 14. Okay, guys, I hope this makes sense so far. I'm going to make another video. I'm going to do one more example of 2 by 2. I'm going to do it a different way, and then I'm going to show you why I'm doing it the different way, because you can't use this method for 3 by 3 matrices. So I hope this helps. I'll make another video here in a second. Thank you.